So I'm going to talk to you about callbacks in multi-threaded code. And so I'm going to talk about three things, really. First is I'm going to do an intro to task-based programming, which is what I mean by that, and is the scenario in which we end up with lots of callbacks. Some of the potential issues that you have when writing such code, and some solutions to those issues. And then I'm going to pull together some of the guidelines that I put together and just give a quick summary of those. So that's a brief overview of what we're doing. So let's start off with what I mean by task-based programming. Well, the key feature is that you've divided your work. You've got this load of work that you want to get done. You're using multi-threaded code to do it because, hey, you've got multiple cores, multiple processors, and you want to make use of it, particularly if you've got something you want to scale. So that, it depends if you want to be able to run on 16 threads if you've got 16 cores, but only 8 if you've got 8 cores, and you want the system to just scale. So you divide your work up into lots of small tasks, and then you submit these to run on some thread pool or other form of executor. And the advantage of this is that then your main application code does not have any explicit thread management. The thread management is delegated to the thread pool or executor, and you just say, here's a task, run it. So, in the first instance, this is great. The thing is that your thread pool has varying properties depending on quite how you've written it, where you've got it from, whether it's something you picked up from a library or whether it's something you've written yourself. The key feature, of course, is that it's going to have multiple tasks per thread, because that's why we're using a thread pool. We're going to reuse our threads, so you start with, it runs a task. When it's done, it picks up another task from the queue rather than stopping the thread and starting a new one. But then the other properties can really vary. You may be able to wait for some of the tasks to finish. You may not. You may be able to obtain a result from your task. You may not. You might be able to cancel some of your tasks or chain continuations on your tasks. One thing that is common to most of the libraries, though, is that you can't have one task wait on another task that's also submitted to the thread pool. Generally, if you that way lies deadlocks, because if you scale down the number of threads, then you quickly find that you've got 4 tasks running on a 4-thread pool. They're each waiting for another 4 tasks which aren't scheduled, and so nothing can run. So there are some thread pools that have sort of dynamic growing mechanisms to allow that, but in general, as a general rule, that's not something you can do. If you want that sort of thing, you need to be chaining continuations. So either you want a thread pool which naturally supports that, or you want to build that on top. As a general thing, thread pools are a special case of a concept called an executor. And executor is simply an object that controls how, where, and when your tasks are run. And this particular terminology has become popular because it's been actively discussed in the C++ Standardization Committee for a number of years now. The standardization proposal is now on its umpteenth revision. It's been through a couple of paper numbers as well, so it's not even continuous. But the current proposal is P0443. With, if you take the PDF of these slides, then that's a clickable link that takes you to the latest version of the paper. And the current proposal allows you to query properties of your executor. So you can say, can I submit tasks that can give me a result back? Can I submit tasks that allow continuations? And so the specifics of those properties are then defined as extension property in extension papers. So like 1244, it specifies those particular properties, but there's other ones as well. And the idea is that it's an extensible mechanism. You can imagine a new property, and then you can query your executors to see whether they support it. And of course, None of the standard ones will, but any that you write or might well do, and potentially libraries will supply executors with a set of properties that they support. But at the base level, all you need is a submit function with a void return. That is enough for anybody. You can build everything else on top of that. It might not be as efficient as if the thread pool or executor had it natively, but you can do it. You can build something that allows you to wait on tasks. You can build something that allows you to cancel tasks, or get the results, or chain continuations. These are something you can build on top. So if you want those properties and your executors and thread pools don't natively provide it, then that's okay. We don't have to panic and say, oh no, the world's coming to an end, we don't have the feature we want. We can build it on. Usually by using something like standard promise and a standard future, in terms of because that allows you to wait, it allows you to get results. If it's an experimental feature from the concurrency TS, then that allows you to chain continuations. So we can build all these facilities on top. So one thing is that comes, the title of the talk is about callbacks, and a callback is when typically you're registering your code to some library, and you say, when some event happens, call me. And you're then not in charge of where your code now runs. The object that you're giving your call to say, run my callback, it's in charge. Sometimes you can specify when you create the object, I want you to use this executor, this thread pool, to run the callbacks. And sometimes you can't. But if you can't, you can always do it anyway, because you can wrap your callback in a little lambda that when it gets called on whatever thread pool or executor the callback chose, the library chose, it says, well, actually, resubmit it on my chosen executor. It's a little bit of a delay, it's a little bit of a two-step dance, but it gives you the control. I want the bulk of my work to actually run on my thread pool, because this is going to be a quick and easy function. And it's not going to occupy whatever thread it is that's actually running this callback for very long. So what sort of issues do we get with asynchronous tasks? There's a few, obviously. Is multi-threaded code? First one is going to be race conditions. There's always race conditions in multi-threaded code. There's also potential issues around reentrancy, because your callbacks might want to access the object which triggered the callback, and so then maybe that can then, there's issues around that. You've got issues around lifetimes, making sure that the objects referenced by your task or callback are actually still alive when it's running. And then you've got the issue you've built of making sure that your system shuts down safely when it's done, particularly if the user's got a great big cancel button and they realize they've just asked to download 300 terabytes of data and they don't want to do that. So, race conditions. Well, we always have race conditions. Like I said, it's multi-threaded code. There's always race conditions, and task-based code with callbacks is no different. The particular new race condition here is that you've divided your work up into lots of tiny bits and submitted them to the thread pool to run. And the thread pool is now in charge of which one gets run first. And so you submit 10 tasks, it picks 4, and it runs those 4. It then picks another 4 to follow on, but it's not necessarily the ones that got submitted next. And particularly then, say it's got on 8 threads, you run it on an 8-thread machine instead, it now picks the first 8 tasks. One of them's really quick, and so the 9th one has started running before the second one has finished. Whereas on a 4-thread system, then you might find that the 9th one doesn't get run until all the first 4 are finished, and possibly even some of the second 4, depending on how things get scheduled. So this is a new and unique race condition just for dividing things up into tiny tasks. So it's something fresh that you need to be aware of. So when I talk about reentrancy, I said you often want to perform operations on data structures. So you've got some object, you register a callback when something happens, and you might want to do something back on that object when you've got your callback, when the callback happens. So this is multi-threaded code, so you're probably going to want to be doing locks. So as your implementation of this class that does the callbacks, you put some nice mutex locks in. This is great. The problem comes, okay, some method is going to run some callbacks. This is going to call back out into your code, your callback code, which says, I want to do something on my class. Oh, look, we're calling back here. We've just deadlocked ourselves. We've tried to lock a mutex we already own. So you need to be aware of this, and we need to do something about it. So, because fundamentally, this is a violation of a general guideline for writing multi-threaded code. Never run user-supplied code whilst you're holding a mutex, because you don't know what that code is going to do. It might either try and lock the mutex you already hold, it might try and lock a second mutex where a different thread is going to lock that mutex and the mutex you already hold in a different order, and so you get deadlocked between the threads, and generally it's just a bad plan. So we have a violation. What can we do about it? The simple first initial solution that might come to mind is to take the callbacks and lock them take a local copy. So you create some storage to hold them, you lock the mutex, you do whatever it was that you needed to hold the mutex lock for, you copy the callbacks, then you unlock the guard, and now you can run your callbacks. So I have my list. If somebody modifies the list in the background, that's fine. If somebody locks the mutex for some other purpose, that's fine. My callbacks are now not run whilst the mutex is locked. So this solves the initial set of problems. But it has downsides. The first immediate downside is if two threads call this function rapidly after each other, so the first one was waiting for the mutex to be unlocked, and then as soon as the mutex came unlocked, then the second one can run it. Now both of those threads are running sets of callbacks simultaneously. So you've got two sets of the same callbacks running. That might be okay, it might not, but it's something to be aware of, and potentially an issue. And again, there's now potential for race conditions within the callbacks, because they're now being the same callbacks run multiple times on multiple threads. So you need to be aware. And a secondary consequence of that is that the two triggers for the callbacks typically had two updates to go with it. And so the update, but now your callbacks are racing. So the callbacks for the second set of updates might happen to run, because the scheduler is non-deterministic. The callback for the second set might happen to run before the callbacks for the first set had run, or interleaved. And so depending on quite the properties of the callbacks, if it's just a void function with void return, then it has to then query the objects, well, what was the state? And so it doesn't do it. But sometimes the callbacks, you're passing data to say about, well, I updated this, and the magic number is now 3. And then you updated it, and the magic number is now 42. Well, actually, and then your callbacks get called the other way around, and it says the number 42 came first in the callbacks. And does that matter? No, how is that? No, I was downloading my file, and well, I had 3 terabytes downloaded, and now I've only got 1 terabyte downloaded. Hang on a minute, what's going on here? No, the data's coming out of order. So again, this is a problem. It's not. Sometimes you can get away with it, and sometimes you can't. And then the third thing is that unregistering the callbacks is a problem, because you've taken a local copy. And so somebody else says, I don't need that callback anymore. And so they remove it from the list. But the thread that's going to invoke the callback has still got it registered in its list. And so now, if that's scheduled after the removal, then you're calling a callback that the other code thinks is no longer active. And that may cause a problem, again, because of the other issues associated with this. It might have lifetime issues. The callback might be accessing something which I deregistered the callback, so it's safe to destroy the data. Hang on a minute, no, the callback's now going to be called. The data is now already destroyed. Bam, undefined behavior. Bad things happen. So it's a simple solution. It has downsides. What can we do about that? One possible solution is to queue up your callbacks. So rather than having you make your modification, it does something that triggers the callbacks to be run. Rather than calling them right then, it sticks them on a queue and say, I've got these callbacks to run. It then has a background thread or another task or something registered to the thread pool that then runs these callbacks in order. And that means that then you've avoided the out of order. No, you don't have multiple sets running together because there's only one thread launching these callbacks. You've avoided the out of order updates because there's only one thread doing them. It's registered them and they're in a single order in the queue. And you do have this potential for dealing with the removal. As unregistering callbacks is now something you can deal with. So let's have another look at our method that does things. We lock the mutex, we do stuff. We go through our list of registered callbacks and we add them to our callback queue. And then we make sure that we actually do have a task running that's going to invoke that callback queue. So to make that, we can do, this is still held under the mutex lock from the previous slide. So if we don't have a task scheduled, then we submit one to the pool, and then we say, yes, we do now. So that's a simple thing. Make sure we've actually got a task running on the pool to run the things. And then when we're actually running them, we can then loop through. We can take the mutex lock, check whether the queue is empty. If the queue is empty, then we say, well, we're done. No, we're going to say we're not registered anymore. This task is going to give up. Next time somebody needs to trigger some callbacks, they'll submit a new task to the queue. Because again, this is task-based programming. We want this task to run as short as possible. And so as soon as it runs out of callbacks to run, it stops. And the next time somebody's got callbacks to run, they get a new task. So we get our first callback from the queue, remove it. We unlock the mutex so that we're not running the callback whilst we're holding a mutex. Then we call our specific callback, this specific entry that we got off the queue, and then we can lock the mutex again, ready for the next check round in the loop. If we're worried about making sure that we're not running callbacks when they're deregistered, you can stick a nice check here just before you call it. Now, has this callback been unregistered? There's various ways of doing that. You can assign IDs to them. You can just check the pointers depending on how they've been registered. But it's now simple because there's one place to check it, and you can just verify, is it still in the master list? Rather than the list of queued callbacks that we're trying to trigger, you can check, is it in the list of ones that are actively registered for all the system? So it gives you a simple place to check. And because there's only one thread running this task at a time, then it makes it easy. There's not the wide possibilities of race conditions that there might otherwise have been.
There's still a race condition here, right? So if you're checking if the entry is still registered, then call that callback between that if and running that callback, there is still a race condition where it might be unregistered.
Yeah, if you just did a simple if, then yes, there would be a potential. If it was just a simple if, is it still registered, run my callback? But it's very easy then to put some, if you've got your callback entry in the master list, you can have some states on it. You can say, it's registered, it's running, it's finished. And so you can, the call that's trying to deregister it, say, well, if it's still running, then I'm done. And so if you check when you do the check, then you can switch it from not running to running as an atomic operation, and then the thread trying to deregister will know to wait. And so it's easy to do because there's just the one place that you have to worry about, rather than multiple places in the code.
There is one of might be another position here. And if you go to previous slide, there is a place where we do something and then call the callbacks based on what we did. Now, there is a do something has a text lock.
Yes.
And then calling the callbacks has...
so here.
Yeah. Calling the callbacks is doing something else. Now, we could have two separate mutexes, so we then get away from the... So there is a do something mutex, and there is a callback mutex. So once you've done something, then you have a call something mutex, which we lock, which would then avoid this situation where callbacks can be deregistered while they are being called. So,
well, so the suggestion for those that couldn't hear was that you could have two mutexes. You could have a mutex that protected doing stuff and a mutex that protected the callbacks. Potentially you could, because this is a way of solving the problem. There are many ways of solving the problem. You still need to be careful not to invoke the callbacks whilst you're holding a mutex lock, because there's still a danger. So there might be a way to do it with two mutexes, which allows higher performance in some cases, but you still need to be aware of that sort of potential. Yes. So, but like I say, I present a solution to problems. It is not necessarily the highest performance. It's something to make you aware that there are ways to, there are problems, there are ways around them, and then you can look at things in your own code and see, is there a better way that works for my circumstances? Okay, so lifetime issues. Dangling pointers and references are bad. We do not want them. They cause undefined behavior and just general disasters. They are also easy to get with multi-threaded code. So, just as a simple example here, okay, we've got some thread pool, we're trying to launch some tasks, we're going to launch some number, and we give them all a unique number so they know what they're supposed to be doing or which block of data they're supposed to access. So we submit to our task, we say run task, and we've got a lambda, and we take it capture so we can reference I in our lambda to say we're going to run task I. Okay. Nice and straightforward. If this was single-threaded code, that would be fine. If this was a for each, that would be fine. But this is not a for each. This is submit to a thread pool. So this reference capture here is evil. That reference capture means that this I here is a reference to this one, which we are now changing in the outer loop whilst it's being accessed from the pool tasks. So that is problem number one. This is just a data race and is straightforward undefined behavior. Problem number two is that, by and large, the reason we're using tasks is because the tasks are going to take longer to run than this little loop. And so our tasks are going to outlive this loop, and so they're going to now be referencing this value I, which doesn't even exist yet. Never mind the fact that it was a data race to access it. It doesn't even exist anymore. So we now have a dangling reference to something with a data race. It's a double problem. Don't do this. In this particular case, you can just change that to an equal sign, say copy. Copy the I into the lambda. It's now a local value. It's perfectly safe. So, general guideline, if you're doing tasks, if you can capture by value, do that. Because that avoids your dangling pointers and references. And then incidental data races. Just, if you can capture by value, do it. And we're talking about task-based systems here, but as a general thing for multi-threaded systems, if you can safely copy the data to your different threads, so then each accessing their own local copy, then it's so much easier to reason about because there's no races, no data races on the data. And potentially higher performance as well because you don't have cache problems each thread's trying to access the same bit of data. So value-based programming, Herb mentioned value-based programming in the keynote this morning. There's a key benefit of C++. Values really help with multi-threaded and task-based code. Capture by value if you can, rather than by reference. And that's not just lambdas, that's everything else that you might mean, shared pointer is still a capture by reference. So if you can avoid having shared access by whatever means, use the values. Sometimes you do want a real reference or pointer to some state from your task. Say you're doing some async I/O, you're trying to load some data asynchronously, you've got some sort of file handle, and you've got an async load data function. If we're at the elf end of file, we're all done. Otherwise, we're going to launch an async read task. We want a reference back to our class so that when we've read our block, we can queue the next to load the next block chunk. So, no, we do need the reference. If you don't have the reference here, then it makes the code really convoluted because somehow you've got to transfer the ownership of the file handle into your callback, and it's possible, it's doable. I've seen code that does it. It's messy and harder to understand. But no, so sometimes the simplest code is just to keep a pointer. But you do need to watch out for problems. So consider a simple function here. We have our class X, and we call async load data. Unless our destructor does something funny to deal with this, we've just launched async tasks, and we've just destroyed our object. We now have dangling pointers. So we need to do something about that. Okay. So, if your task holds a pointer or reference, then you need to make sure that the data is alive when the task is run. And one possible way is to give the task ownership of the data. If the task owns the data, then the data is not going to go away. The second option is you can wait for your tasks before you destroy the data. You say, well, I have some data, I have some tasks that run, so I know that I've got my tasks running. I'm not going to destroy the data till I know that all my tasks have safely completed. So in our destructor for some class on the previous slide here, if our destructor waits for the tasks to finish, we don't have a dangling pointer problem. Alternatively, if the tasks own the data in some way, then we don't have a dangling pointer problem because the tasks are still running, but the data is still alive because the tasks own the data. And the other thing, which applies to both of these, is that you might want to set a shutdown flag to stop new tasks happening. Okay? Somebody clicks, load the async data. This is great. Oh dear, it's a 3 terabyte file. I didn't want that, cancel the task. So shut down your application. Oh no, it's still running. 5 days later, it's finished downloading its 3 terabyte file. In the meantime, it's consumed all your bandwidth on your broadband. That wasn't what you intended. You really wanted it to stop. So you can set a shutdown flag to stop new tasks generating and to potentially tell the ones that are running, actually, it's time to stop. The user has signaled in some way that we don't want to run anymore. So, shared ownership, C++. The most straightforward way of shared ownership is to use a shared pointer. If the tasks own the data with a shared pointer, then we guarantee that the data is only destroyed when the last shared pointer instance goes away, and we don't get the dangling pointers. So how can we make that work here? Well, rather than having the file handle itself be a member of our class, we put it in a data object. We allow shared from this, and then we have a shared pointer to the object in our outer one, and then we call into the data object calling the async load data. So we've essentially moved the bulk of our function from the outer one directly into the data object. So then, when it spawns the task, it can get a shared pointer to itself. It can transfer that into the task that's being set as the callback. And then it can process the block chunks and schedule the chain task. This sort of code you actually do see a lot in code that uses Boostazio, because we're wanting little bits of, we're doing async I/O, we get little bits of data coming back, we then want to schedule the next task, making sure that everything keeps referenced to the relevant core data and that everything's kept alive. You pass around shared pointers, and then you end up with little bits of callbacks that look like this. There are probably other ways of doing it, but this is something I've seen quite a lot. So this avoids the dangling pointers, but it still avoids, we still have this potential for dangling tasks. We can still have our 5 terabyte download going on in the background, because each task, it retrieves this little bit of data. It says, oh, schedule the next one. The data block's still alive, it's all fine, but the task keeps going. We end up with a continuous callback chain until the outer task is done. And obviously, depending on what our system does, sometimes the tasks might never be done, because it might just be what amounts to an endless loop. Because it's intended to be a continuous monitoring sort of application, and so there's always data to process, and so the task keeps going. Every task schedules the next one. The data's fine, but the application doesn't shut down. So we still need a way to manage orderly shutdown. Just as an aside, you might think that using weak pointer in your tasks is just as good, in fact even better, because then if the outer structure goes away, then this provides our shutdown signal. The outer structure goes away, the master shared pointer is gone, and so if the task only has a weak pointer, then when it tries to convert that to a real shared pointer, then that's great. If the outer block's alive, then it can do so, and if the outer block is gone, then it can't. So we call our dataref.lock to get a shared pointer from the weak pointer, and then we do our processing. Yes, this does have that sort of property, but it allows a new, unique sort of race condition. Running task 1 holds the rate, tries to get the lock, and it succeeds. It now owns a shared pointer to the data. On thread 2, we clear that. We're trying to destroy our outer object, so we clear our shared pointer, our master shared pointer, and the only shared pointer to our data is now the one held by the task. The task is now the one that destroys the data object. If you weren't expecting that, that can cause problems, because the destructor for the data is now run on your task rather than in the outer block. So it's potentially on a different thread, and that thread might not be expecting to be the one that destroys the data. I've seen code where the destruction for the data object tried waiting for tasks. This did not go well. So don't use weak pointer. Just bite the bullet and use a shared pointer if you're going to try and share the data with the tasks. Or wait for the tasks to finish so that the data is just kept alive anyway. Yes, there's a question.
Isn't it the same problem with shared pointers? Because in the end, the task...
Yeah, so yes, so the question is, do you get the same problem with normal shared pointers? Yes, but if you've got a shared pointer, then if you're using a shared pointer straight off the bat, then you're already aware of that. I've got a shared pointer object, and because I know I own a real reference, and at some point it's going to be the way, and I might be the last one. You're taking that on up front. With weak pointer, it's not immediately obvious that actually you're doing that, because you're thinking, oh well, if the shared pointer's gone away, I won't get an object and I can't do it. But it's the race condition that catches people out. So yes, if you had your destruction of the data object doing something like waiting for tasks and you just had a normal shared pointer, then you can still get that problem. But it's more apparent to you when you're writing the code, whereas with weak pointer it's a little bit less obvious. And it doesn't, fundamentally it doesn't gain you anything. Okay, so if we're going to shut down safely and stop our 5 terabyte download, we need to do something to signal to the tasks, A, if you're running, please stop, because we're done, and don't start any more tasks, please. In C++ 20, we're going to have some classes to help with that. We're going to have a stop source and a stop token. Now, you can use stop source all on its own. It provides a means of saying, no, I want to stop, and has somebody requested that we stop? And a stop token is just the checking side of that API. It's I've got a stop token. I can't ask to stop. But I can say, has somebody requested that we stop? So, no, there's two parts of the same thing, and the stop token, like I say, is just the read side. So we can stick a stop source in our data, and then when we try and do the load task, then we can say, if our flag says with stop's been requested, then we just, okay, we're not going to actually do anything. We're not going to call into the file handle to do an async read. We're just going to stop now, and then in our destructor of our class, we can request a stop. So after we do this, then we won't get any new tasks spawned. But if this one is still running, because there was no stop was requested when we started it, but it's now stuck here in this ... doing something, then it's going to keep running. So no, that doesn't wait for the task. It just tells them to stop. And so our 5 terabyte download will just do the next chunk and then stop, however big that chunk was. So no, there isn't. So the tokens don't provide any forms of waiting. It's just a signal. So you request a stop, and you can check, has it been requested? If you don't check, it does nothing, and there is no waiting facility provided. That waiting is not part of this API. So yes, in some ways it can be a wrap around an atomic bool, but it's a little bit more than that, because it also allows callbacks. So your async, it was going to register, it registers with the file handle, do me an async read, and so then we say, but that might take some time, and we're trying to shut down quickly when we've asked a signal to stop. So we can say, we want to register, can have a stop callback in our data, so that when we register, when we start the task, we register the callback, and the callback, we need a stop token to register the callback, incidentally, and the callback then says stop the async task that's running. It tells the file handle to stop the async task, and then it's up to that, however it deals with that internally. On Windows, then you might use something like cancel IO to cancel pending IO. On other systems, you might use something else. Notice that it captures this here. We're inside the data class, and it's capturing this by value so that we can reference the file handle and things that are inside. But we know that that's going to be safe, because the outer callback owns the reference to data. So this callback is done by the time we hit the closing brace of this function. Because then when you hit the closing brace, so the stop callback goes away. So we don't need to worry, and and the data is owned by the shared pointer that we had when we registered the outer task, and so we don't need to worry. It's only when the data is destroyed that that we would worry, and the callback will have gone away by that point. This isn't actually in the C++ 20 draft yet. It's slowly making its way through the committee. The proposal is online at P0660. It's currently on revision 9 because it's slowly making its way through the committee, and every stage people say, oh, well, the wording's not quite right, so we need to improve it. So fingers crossed at the next WG21 meeting, it will actually make it to the working paper. There is a sample implementation, so you don't have to wait for your standard library implementer to provide it. So Nikolai Jasudis has put it up on his GitHub page. And if you can't use it and you don't need the callback facilities, then actually you can use an atomic bool for lots of this facility. So, it's a nicer API than an atomic bool, but yeah, lots of the time, all you need is the bool. Okay, so if we're going to try and shut down our task-based system in an orderly fashion, and we don't want dangling pointers and we don't want dangling tasks, then we're going to have to wait for our tasks to finish. It really comes down to that. If you want to make sure that everything's done and dusted and everything's finished properly, you're going to have to wait for it. Obviously, we want to signal our tasks to shut down so that they shut down as quick as possible. We want to avoid spawning new tasks so that we don't have to wait for them too, but we do need to wait for everything to finish if we want to shut down in an orderly fashion. And there's multiple ways we could do that. We could store futures from each task and wait for each of the futures. This will work, it's perfectly fine, but if you're just using the standard library as it stands, then all we've got is serial waiting for the futures. We don't have a wait for all of them. We just have wait for this one, then wait for that one, then wait for the third. And if you do it that way, then you wait for a task to finish, so your thread gets suspended. The other thread is running, this is fine. It finishes its task, the OS wakes you up and says, you're awake now, you're done, your wait was finished. You say, oh yeah, but I want to wait for something else. And you do this 1,000 times. This is just a lot of waking you up, the OS waking up your thread just to say, no, actually, I'm waiting for something else. So it's not ever so effective. If you've got something that provides the concurrency TS, then you can use their when all facility. So you can say, when all these futures are ready, then wake me up. And you can wait for that. But if you don't have that available, then you have to do serial waiting, and that's inefficient. And the other thing, of course, is you've got to store these futures somewhere. If you're going to wait for them, you've got to be able to access them in order to do that. And that means you've got to have some form of container. And that means that when you spawn tasks, you've got to put the future in the container, which means it needs synchronization. So it's not, it's a working solution. It's not necessarily the best solution. Another option is to count your tasks. When you spawn a task, increase your counter. When it's done, decrease the counter. And when the count is 0, they're all done. Marvelous. Of course, your counter needs synchronization, so this, again, it's can't just use an unsigned long. You actually have to do, at least an atomic unsigned long. And you want to wait. And so you probably need something else, possibly a condition variable. Although, again, in C++ 20, then atomics are allowing waiting for the value to change under some circumstances. So, potentially you can use that. But there is definitely less overhead than futures. So if you don't need the future for the result capability, you are just using it for the waiting, then this is more efficient because you don't need a vector of futures to hold that. You can just use an atomic variable. And the synchronization is therefore less, and you still need to do the synchronizing on the counter, but it is less overhead. So if you don't need the futures, then this is a beneficial change. Again, there might be better ways. This is a possible solution to the problem, but it does work. So a simple example of this is, well, rather than using atomics, because using atomics and condition variables actually is messy, and you end up needing a mutex anyway, so we'll just go ahead, we'll use a mutex and a plain integer. We'll also have a flag to say that stop has been requested, and then we use this, you can use this to wrap any existing executor or thread pool. Now, I've chosen a concrete type here, but you can make it a template and then it would wrap anything. So you submit to your counting executor rather than whatever the underlying one you wish to use. And then when you try and destroy your wrapper, then it will wait for all the tasks to finish. So in the destructor, you lock your mutex, you set the stop flag, and then you just wait until the count of active tasks is 0. And then when you submit a task, you lock your mutex. If the stop's been requested, then actually we don't submit it, and we just return false to say, no, this didn't happen. Then we increase our number of active tasks, and then we submit it to the underlying pool. But we don't submit the raw task, we submit a lambda that wraps it, we call the raw task, and then we lock our mutex and decrement the active tasks, and if it's 0, then we notify. And in order, again, we have to capture this so that we can lock our mutex. But this is again going to be safe to capture this because the destructor for the counting executor waits for the tasks. So it will wait until active task is 0 and our notifies have happened. And because the mutex is locked for that check, and the mutex is locked for the whole of here, then you know that there can't be a pending task running, and the counter have got to 0. And just like in this case, if you wait for all the tasks to finish, you may not need to share the ownership with the tasks after all. You can just capture this as a raw pointer because you're waiting for the tasks to finish. So you know that there aren't going to be any tasks running that can access your object because you've already waited for them to finish before your destructor finishes. So that then potentially simplifies the task code. You don't have to worry about the shared pointers, and you certainly don't have to worry about weak pointer problems. So, guidelines. First one, obviously, do not call user-provided code whilst holding a lock. Standard guideline for multi-threaded code. Don't do that. Again, watch out for dangling pointers and references. Now, again, I repeat, this is a particular problem with task-based things because you've got all these little bitty things that are running, and it's very easy for them to keep running beyond the code that spawned them, and beyond the lifetime of the object. So you need to pay attention, particularly if you use lambda captures. It's very easy when you're using a lambda to use that nice little ampersand sign to capture by reference to the enclosing scope for local variables, which obviously then are really prone to being dangling references, and also then to members of your outer object if you haven't got some means of making sure that things stay alive. So though lambdas are the easiest way to achieve the dangling references, they're not the only way. You need to watch out for anywhere within your task where there is a pointer or reference to something that the task doesn't own, and that therefore you need to pay attention to the lifetime of. The solution to that, therefore, as well as paying attention, is to copy values where you can. Because, again, like I said earlier, if you copy values, you don't have race conditions on them. You don't have data races. You don't have to worry about dangling pointers and the lifetime issues because the copy is there in the task. The task owns the value, so you don't need to worry about that sort of thing. And use shared pointer to manage lifetimes where the task can't have a copy, where you do need a real reference. Use stop token and stop source to avoid dangling tasks, to tell them to stop, so that they don't just keep going ad infinitum and having a whole system that's running in the background, and then wait for things to finish. And just make sure that your system as a whole has a clean means of shutting down. Okay, I'm just going to talk a little bit about alternatives. I've been mostly saying about task-based systems and callbacks. It's not the only way of writing multi-threaded code. I see the classic old-school method is to use explicit threads. I say this is old school. Don't do it in new code, really. No, but it's there. You might have explicit threads, so use that. A preferred option, which in my mind is sort of equal footing up there with task-based systems, is to use actors and message passing. See, anyone who works with Erlang, this is what Erlang's all about, but you can do it in C++ too. You can have a set of actors which each run on their own independent threads, and then you don't do any explicit shared data. You just pass messages between them, and so all the synchronization is then done in the actor library in the message queue, and you don't need to do any explicit synchronization yourself. So this is a very powerful abstraction, but you need to, it's a whole system thing. You need to design your system around it, and if what you have is a callback-based system, like lots of async I/O code ends up being, but also lots of other system ends up with callbacks and tasks, then migrating that to actors is a big job. So it's not necessarily something anyone can use. Alternatively, if your problem is susceptible to it, use the standard library parallel algorithms. Then you don't have to write any explicit synchronization and sharing code yourself. Let Marshall do it. or the standard library maintainer for whichever standard library you use. Because the standard library is there and it works and it's well tested, so it avoids you having to write the problematic multi-threaded synchronization code. So if your problem can be reduced to a for each over a bulk load of data, then use the standard library. And obviously, lots of the algorithms are efficient when done on parallel processes. I think there's only a few algorithms in the standard library that don't have parallel algorithms overloads, but whether or not any given one is efficient for your data does vary widely. And then, of course, now they're in C++ 20 working paper, it would be remiss of me to say, to not mention coroutines. If you have a multi-threaded scheduler for your coroutines, then they can make your code look a lot simpler, because actually under the hood, it's callback-based code with lots of little tasks. But those tasks are coroutines, and you just write it straight line code with a few coawaits here and there. And it's simpler on your end, but whoever writes the library has to do all the synchronization. And so again, if you can find somebody who's written a nice coroutine multi-threaded library for you, or you're willing to do that for your company as an internal library maintainer, then that can make the application code a lot simpler. And it has lots of the benefits of using the callbacks and the task-based code whilst actually simplifying the user code. So there's a lot of potential there for improvements. Okay, so my book, the second edition, is now finally in print. After waiting for... After waiting for a while to actually go from my final submission of the PDF to the printing in February, it's finally in print. So I'm doing, immediately after this, at lunchtime, I'm going to do a signing session. So if anyone, and I do have some for sale if you haven't already got a copy. So, so yes, and then also just a quick plug for my multi-threading library, which does provide actors. It doesn't provide coroutine scheduling, but it does have an actors set and concurrency TS. So you can there is that when all the futures are ready facility as well. That leaves us plenty of time for questions.